Welcome back, 8th grade Apologia, Physical Science, Week 15, Day 4, textbook pages 256 through 262, notebook pages 210 through 212. Okay, before we get started today, I just wanted to let you know that this is some pretty advanced material. This is some pretty advanced physics, more like high school level physics and college level physics. But it's great that you're going to get to hear about some of these forces and some of these theories now, so that when you hear them in high school or college, you'll at least be somewhat familiar with what they're talking about. All right, so having said that, let's get started. All right, fundamental forces. Believe it or not, physicists think that there are only 4 different kinds of forces in creation: the electromagnetic force, the strong nuclear force, the weak nuclear force, and the gravitational force. These forces are called the fundamental or universal forces because all forces in creation can be traced back to one of them. I will give you a brief overview of these forces. You will learn more about them in your high school chemistry and physics courses. All right. Let's talk about the electromagnetic force and some examples. The electromagnetic force exists between particles with electric charge. Electric force and magnetic force are 2 different aspects of the electromagnetic force. The electromagnetic force is the only force that can be either attractive or repulsive. Electric forces act between charged objects or particles whether or not they're moving. Remember from Module 2 that protons and electrons are charged particles. You know that 2 positively charged objects, like 2 protons, they will repel each other, as do 2 negatively charged objects, like 2 electrons. You also know that 2 objects with opposite charges will attract one another. Opposites attract. Have you ever taken clothes out of the dryer that were stuck together, and when you pulled them apart, you heard and felt the static charge? That's because some clothes lose electrons easily in the dry heat of the dryer and become positively charged. Remember, if they lose a few negative charges, they would be positively charged. Others gain electrons easily and become negatively charged. Then the oppositely charged clothes cling together because of their electric attraction. All right, so now let's look at the magnet example in figure 7.31. The magnetic force acts between moving charged particles and on the poles of magnets. Every magnet has 2 poles, a north pole and a south pole. Opposite poles attract one another and like poles repel. Look at 7.31 up here. The north pole of the bar magnet is attracting the iron filings attached to one of the poles of the red horseshoe magnet. That is your clue. If the poles are attracting each other, the pole on the red magnet must be south. If you move the bar over to the other side of the red horseshoe magnet, the iron filings would be repelling each other. Much in the same way, have you ever played with magnetic toys, like the train shown in 7.32? If you have, then you've likely noticed what happens when you try to put 2 poles near each other. Each car in the train set has a north pole on one end and a south pole on the other. If, when you try to connect 2 cars, you feel them pushing apart, you know you have 2 like poles. To connect them, just turn the car around and they'll quickly pull together. Electromagnetic force shows itself in many ways in your day-to-day life. This force is responsible for holding atoms together because of the electromagnetic attraction between protons and electrons. Light is an electromagnetic wave. The electricity powering the appliances in your house occur because of electromagnetism, and these examples just scratch the surface. The electromagnetic force is a fairly strong force. There is only one fundamental force stronger than this, and you will learn much more about the electromagnetic force in the next module. Okay. So that's the electromagnetic force. Let's move on to the nuclear force, which is comprised of the strong force and a weak force. All right, so nuclear forces. Remember when we discussed the nucleus of the atom? It's composed of protons and neutrons. Did you ever wonder why the repulsive electromagnetic force of the positively charged protons didn't cause the nucleus to fly apart? Well, that's where the nuclear forces come into play. There are two nuclear forces, the strong force and the weak force. All right, let's start with the strong force. As its name implies, the strong nuclear force is the strongest of the four fundamental forces. However, it only acts over a very short distance, approximately the diameter of a proton, 10 to the negative 15th meters. That's tiny. Although the strong force only acts over a very small distance, it is about 100 times stronger than the repulsive electromagnetic force. This is the reason that protons do not repel each other. The strong nuclear force overcomes the force of repulsion at distances inside the nucleus and holds the protons and the neutrons together. Once the proton, neutron, and electron were discovered, scientists conducted many experiments to try to figure out how the nucleus would stay together. Again, because the nucleus only had the positive protons in there. According to the current model of the atom, called the Standard Model of Particle Physics, protons and neutrons are made up of even smaller particles called quarks. All right, so this is new. Quarks that are held together by force-carrying particles called gluons. A quark is a subatomic particle scientists theorize to be among the basic units of matter, one that cannot be split into smaller parts. But of course, they're still looking for smaller ones. You will learn much more about this in high school and college chemistry and physics, but I will tell you that the predictions made by this theory have to date been experimentally confirmed with good precision. All right, so that's the strong force. And now today we talked about quarks and gluons. All right, the weak force. The other powerful force in the nucleus is the weak nuclear force. As you can tell by its name, the weak force is weaker in strength than the strong force. Like the strong force, the weak force acts over a very small range, about 10 to the negative 18th meters, and is explained by the Standard Model of Particle Physics. But unlike the attractive electromagnetic and strong forces, the weak force plays a bigger role in particles breaking down or decaying. As a result, the weak force governs certain radioactive processes in atoms, in which one type of quark changes into another type of quark. Changing a quark in this way can cause a proton to change into a neutron or vice versa. Now, remember to chemistry, if a proton is changed into a neutron, then you have changed an atom of one element into an atom of a whole different element. The weak force plays an important role in nuclear fusion, which is the reaction that powers the sun and hydrogen bombs. All right, the last one. Gravitational forces. We've talked about that a bunch here, but let's figure out a little bit more. We've already talked a bit about the force of gravity. Gravity is the force that causes objects to have weight. It is probably the easiest one to recognize, so much so that you likely take it for granted. But did you know that gravitational force is the weakest of the four fundamental forces, and it is surprisingly hard to understand? Even today, scientists are not exactly sure what causes the gravitational force. Now, we have two major theories that try to explain what gravity is, but we really do not know which, if either, is even correct. We still have so much to learn about the gravitational force. Okay. Even though we still have a lot to learn about gravity, we have come a long way in understanding this perplexing force. At one time, scientists did not even know that the gravitational force that causes a ball to fall to Earth is the same as the force that holds the planets in orbit around the sun. It took the brilliance of Sir Isaac Newton, surprise, surprise, to show that gravity is a universal force that applies to small things near the Earth's surface, as well as large things such as the planets. All right, so there's good old Sir Isaac Newton. In fact, Newton developed an equation, which we call the Universal Law of Gravitation, that allows physicists to calculate the strength of the gravitational force between two objects. This equation is shown in figure 7.34. Don't worry, we will not need to know how to use this equation in this class, but we can discuss the concepts of the law. All right. Basically, Newton's law of universal gravitation states that every object in the universe attracts every other object. And what does that really mean exactly? Well, when you place two wooden blocks on the table, they are actually attracted to one another by the gravitational force between them. So why don't they just move towards each other? Remember I said the gravitational force is the weakest of the fundamental forces. Well, the gravitational force is so weak that it cannot even overcome the friction that exists between the blocks and the table. As a result, the blocks stay stationary. Not because there is not gravitational force of attraction between them, but because the attraction is so weak that it cannot overcome the static friction that's keeping the objects in place. All right, that's a lot of information. Now, when we talk about huge masses, like that of the Earth and the Moon, shown in figure 7.34, that is when we see gravitational force exerted. Look at Newton's equation. You see that the masses of the two objects, m1 and m2, are in the numerator, indicating that the gravitational force between two objects is directly proportional to their masses. This means that the strength of the gravitational force increases as the mass of either object increases. The greater the mass of the objects, the greater the gravitational force between them. All right, let's hear. Notice A and B. When the mass of the orange ball is doubled, the gravitational force of attraction that each mass applies to the other also doubles. Now look at the distance r in equation 7.34. So let's go back here. We have r. It is squared and in the denominator. This means gravitational force is inversely proportional to the square of the distance between the objects. So look again at figure 7.35, only this time take notice of A and C. When the distance between the blue and orange ball doubles, the gravitational force between them decreases by 2 squared, or 4. In other words, the gravitational force is 1/4 as strong when two objects are moved apart twice the original distance. Even though gravity is the weakest fundamental force, it is the most effective force over long distances, especially for massive objects. Think about that for a minute. Even though the force of gravity decreases with distance, the planets stay in their orbits around the sun because of the gravitational force. The mass of the sun is about 300,000 times the mass of Earth, so the sun's gravitational force is strong enough to keep Pluto in orbit. Gravity holds you to Earth, it keeps the moon in orbit around Earth, and it causes the oceans to bulge at high tides twice a day. Yet it is the weakest fundamental force. Think about this. We don't often realize that when we drop a ball, Newton's law of universal gravitation states that the Earth exerts a force of attraction on the ball, and the ball exerts an equal force on Earth. What? That may be hard to grasp. Okay, so we know that the Earth attracts the ball because we see the ball fall when we drop it. But the ball exerts an equal and opposite reactive force on Earth. Newton's third law, remember we just learned it? So the Earth rises towards the ball. Well, why don't we feel the Earth accelerating toward the ball? Well, Newton's second law says that the force applied to an object equals the object's mass times its acceleration. Since the forces of the ball on the Earth and the Earth on the ball are equal, and because the mass of the Earth is so large, the resulting acceleration of the Earth is really tiny. So since the mass of the ball is so small compared to the Earth, we definitely notice the ball's acceleration towards Earth, but we can't even detect the Earth's acceleration towards the ball. Just something to think about. All right, so here is one of my favorite things to talk about. General Theory of Relativity by Albert Einstein. But first, let's back up and get into the other theory of quantum gravity. All right. What causes gravitational force? At the beginning of the section, I told you that there were two major theories that attempt to explain gravity. But we don't know which, if either, is even correct. Well, I want to briefly tell you about them. Okay. The first theory is called quantum gravity, and it attempts to explain gravity at the smallest scale, called quantum mechanics. Remember the quantum mechanical model of the atom from Module 3? Well, the quantum gravity theory attempts to explain the gravitational force as interactions of subatomic particles. Quantum theorists postulate that a small force-carrying particle called a graviton is responsible for the force of gravity. Keep in mind that there is no direct observable evidence of a graviton at this point, but since scientists have been able to gather experimental evidence that describes the other three fundamental forces in terms of quantum mechanics, the standard model of particle physics, it seems like a possible explanation. All right, so that was quantum gravity. The other theory was developed by Albert Einstein in 1916. Einstein proposed his general theory of relativity, which attempts to explain a different way of looking at physics. The details are far, far beyond the scope of this course and even a high school course. But one of the byproducts of Einstein's general theory of relativity was an original explanation of what causes the gravitational force. Okay. Einstein's theory states that space is not always the way it appears. You know that the Earth is round, even though it looks flat as you look out across a field to the horizon. In the same way, Einstein postulated that although it does not appear to change at all, space actually bends in the presence of an object with mass. All right, so look at 7.36. This is an illustration of the orbit of Earth around the Sun, according to General Relativity. The blue graph paper, like substance, represents space. General Relativity describes space like a geometric framework in which massive objects could alter or bend that geometry. And if that isn't hard enough to wrap your mind around, the theory also says matter that bends space also bends time. Notice in the figure how the massive sun distorts space enough to create a sort of well around it. A planet such as Earth will travel around the curve in space created by the mass of the sun. Alrighty, so in the general theory of relativity, objects do not move towards each other because of a force of gravitational attraction, but because they are following the curve of space around an object. If Einstein is right, then gravity is not really a force at all. It is instead a consequence of how mass bends space and time. Einstein developed some highly complex mathematical equations that have correctly calculated the movement of objects such as Mercury. While these equations are far too complex to discuss, the basic premise is that mass of an object tells space how to curve, and space tells a mass how to move. Well, is Einstein right? Well, we aren't really sure. The general theory of relativity has a lot of success in explaining things about space that could not be explained before. Most physicists admit that Einstein's explanation is better right now, since it at least has some direct evidence supporting it. In fact, there are some who postulate that both theories are true. At the same time, of course, it is possible that neither theory is true. After all, the history of science is filled with theories that seem to have a lot of evidence supporting them, but were later found to be wrong. All right. That was a bunch of big information. All right, summing up, you experience forces everywhere in creation. Scientists are still discovering things about the interactions between matter. If this topic interests you, you will definitely want to take a physics course in high school because we have only scratched the surface of the fascinating topic. Perhaps you will help to bring the particle and general relativity theories of physics together. All right, on your own, 713, which universal force can repel as well as attract? That's an easy one. Electromagnetic force is the only force that can both attract and repel. And last, on your own 714, which universal force acts to hold the nucleus together? That's an easy one too. The strong nuclear force acts within the nucleus to hold it together. All right, see you in class.